We are moving on to section 4, which is looking at gas laws and chemical reactions, and you'll be able to apply gas laws to study the stoichiometry of reactions. Many industrial important reactions involve gases. Two examples are the combination of nitrogen and hydrogen to produce ammonia, like this, and the electrolysis of aqueous sodium chloride to produce hydrogen and chlorine. If we want to understand the quantitative aspects of such reactions, we need to carry out stoichiometry calculations. Hydrogen gas is produced from the reaction of lithium and water, and that creates hydrogen gas. What mass of lithium is required to produce 23.5 liters of hydrogen gas, so that's a volume, at 17 degrees Celsius, that's a temperature, and a pressure of 243 millimeters of mercury, that's a pressure. We want to get the mass of lithium. Well, we're going to need to use some stoichiometry because, remember, ideal gas law only works for gases. So if I know volume, temperature, pressure, and R for hydrogen, I can get moles of hydrogen. I can find out N for hydrogen. And if I know moles of hydrogen, I can obviously get to moles of lithium. And if I know moles of lithium, I can get to grams of lithium. So let's do our ideal gas law first to solve for hydrogen. I wrote down my knowns. Again, I'm trying to find the mass of lithium. Let's get N for hydrogen. N is equal to PV divided by RT. So I took my pressure times volume divided by R times T, and I got 0.9648 moles of hydrogen. My next step, going from moles of hydrogen to moles of lithium, and then moles to mass. And if I look at my balanced equation, for every 1 hydrogen, there's 2 moles of lithium. So that's my ratio. Make sure that your units are diagonal from one another to cancel out. And since I have moles of lithium on top, make sure that for 1 mole of lithium, we have our mass is 6.941 grams of lithium on top. And if you plug and chug, we should get 13.4 grams of lithium. This problem tells me that I have 15 grams of sodium reacting with water. What volume of hydrogen gas is produced at 25 degrees Celsius, so that's a temperature, and a pressure of 1.10 atmosphere, so that's a pressure. I want to find volume. Well, in order to find volume, I need to know P, this is V. We need to know N, we always know R, and we're given T. So, how do we get the moles if I'm starting with grams of sodium? Well, hopefully we can use some stoichiometry. I'm starting with that grams of sodium, so let's go grams to moles, and then moles to moles. That will give me my N, my moles of hydrogen gas. That will allow me to solve for V. PV equals nRT. I'm going to solve for V, so divide both sides by pressure. So N times R times T, all divided by P. If I plug and chug, I should get a volume of 7.26 liters of hydrogen gas. The next section is about gas mixtures and partial pressures. The air you breathe is a mixture of nitrogen, oxygen, argon, carbon dioxide, water vapor, and small amounts of other gases. Each of these gases exert its own pressure. And atmospheric pressure is the sum of the pressures exerted by each gas. The pressure of each gas in the mixture is called its partial pressure. Now, John Dalton was the first to observe that the pressure of a mixture of ideal gases is the sum of the partial pressures of the different gases in the mixture. This observation is now known as Dalton's law of partial pressures. Mathematically, we can write Dalton's law of partial pressures as, saying the pressure from gas 1 plus the pressure from gas 2 plus the pressure from gas 3 is equal to the total pressure. Here's a little picture example. I have nitrogen in this container exerting a pressure of 186 millimeters of mercury. I have oxygen in this container exerting a pressure of 93 millimeters of mercury. And when I mix the two together, my 0.01 moles of nitrogen from there and my 0.0050 moles of oxygen, I add them together and I just add up those two pressures. 186 plus 93 would give me 279 millimeters of mercury. Additionally, for a mixture of 3 ideal gases in a given volume and at a given temperature, we can calculate the total pressure if we know the total number of moles of a gas in the system. We'll just use PV equals nRT, but to get that total pressure, we need that total N. So they just derived that from PV equals nRT, and to get P by itself, they divided both sides by V. So P is equal to nRT all divided by V. For a mixture of gases, it's convenient to introduce a quantity called the mole fraction, X, which is defined as the number of moles of a particular substance in a mixture divided by the total number of moles of all the substances present. Mathematically, the mole fraction of a substance A in a mixture with B and C is expressed as, there's my moles of A divided by all of the moles from A, B, and C. So it's finding the part divided by the whole. That's what a mole fraction is. If I rearrange it, so I'm going to multiply like this and multiply like that. So I would have NA, so my moles of A is equal to X of A times N total. We rearranged it to solve for N total. So I'm going to divide both sides by X of A. So we have N total is equal to N of A divided by X of A. All we did was rearrange this equation to then plug it in up above into this N total to get this guy. And this equation tells us that the pressure of a gas in a mixture of gases is the product of its mole fraction and the total pressure of the mixture. In other words, the partial pressure of a gas is directly related to the fraction of particles of that gas in the mixture. For example, the mole fraction of N2 in air is 0.78. So at standard temperature and pressure, its partial pressure is 0.78 or 590 millimeters of mercury. If you think standard temperature and pressure, at standard pressure, that's 1 atm. So if XA, so the mole fraction was 0.78, times it by that total pressure, which was 1 atmosphere, 0.78 times 1 is 0.78. And then if I wanted to convert it to millimeters of mercury, I would say 1 atm on the bottom to 760 on top to get that 590 millimeters of mercury. Here's an example problem where we have halothane C2HBrClF3. It's non-flammable, non-explosive, and non-irritating gas that's widely used as an inhalation anesthetic. The total pressure of a mixture of 15 grams of halothane vapor, 23.5 grams of oxygen gas, is 855 millimeters of mercury. What's the partial pressure of each gas? First, we need to find our mole fractions. We were given grams of halothane and grams of oxygen. So I'm going to go from grams to moles using those molar masses. I got mole of halothane, mole of oxygen. To find their mole fraction, remember it's part divided by whole. So I added the moles of halothane and moles of oxygen to get total moles, and that's my denominator for both of these. I'm going to take my moles of halothane divided by total to get my mole fraction of halothane. I'm going to do the same with oxygen. I took my moles of oxygen divided by total moles. That's my mole fraction for oxygen. Now to find the partial pressure of each gas, we're going to use that equation. The partial pressure of A is equal to the mole fraction of A times the P total. We were told the P total was 855 millimeters of mercury. So I'm going to take that first mole fraction for halothane and times it by 855. And that gave me 80.2 millimeters of mercury. Then for oxygen, I'm going to take the mole fraction of oxygen, which we found right here, times by that total pressure. And I got oxygen's partial pressure. Let's look at another problem. That halothane-oxygen mixture from that last slide is placed in a 5-liter tank at 25 degrees Celsius. What is the total pressure in millimeters of mercury of the gas mixture in the tank? And what are the partial pressures of the gases. On that last slide, we calculated how many moles of halothane and how many moles of oxygen we have. So we know the N value of each reactant. And we were given volume, and we were given temperature, and we know R, so we can find the P for each one of those reactants. To find P, PV equals nRT, I'm going to divide both sides by V. So nRT divided by V. I took my N, my moles of halothane, times R, times the temperature, I put it into Kelvin, divided by that 5 liters. So the pressure exerted from halothane is going to be 283 millimeters of mercury. Now remember, when I got my answer, it was in atmospheres. I had to convert from atmospheres to millimeters of mercury because it asked for it. Then I'm going to do oxygen. I took my moles of oxygen from the previous slide. So N times R times T, all divided by 5 liters, and I got 3.59 atmospheres. Atmospheres to millimeters of mercury to get 2,730 millimeters of mercury. So I know the pressure exerted from the halothane, I know the pressure exerted from the oxygen. So to find the total pressure, I'm going to add together the pressure from the halothane and the pressure from the oxygen. Add those two numbers together to get the total pressure. So we found each individual partial pressures and the total pressure.